With the incorporation of climate model data into engineering processes being something new for this tool, we've been asked by the engineering community to provide a bit of a step-by-step guide. This includes some clarification and guidance for how we would recommend you utilize the data, possible second steps and considerations to make sure that it's being utilized accurately and correctly in your workflows, and a place to come back to when you run into trouble or need to see something new. So you'll see down below in the description, in the doobly-doo, that we've got some links to various chapters if you're already familiar with the tool, and to help you come back and reference in the future.
I'm an engineer, interested in predictions about future climate for Bethel, Alaska. I'd like to understand how different air temperature inputs might yield different thermal modeling results, and perhaps help me design for enhanced climate resilience. I heard about the Arctic EDS from a colleague, and I think that the Arctic EDS data might help me. In my case, I'm mostly interested in freezing and thawing indices for Bethel, Alaska specifically. I'm new to the Arctic EDS, so I'll start by focusing on the freezing index. Since I'm not a climate scientist, it's important for me to get familiar with some of the terminology used in the Arctic EDS. On the Arctic EDS homepage, I see an introduction explaining the purpose of this platform. Then I'm also exploring this glossary so I can understand terms like emissions scenario and downscaling, which I realize are crucial to interpreting the projections accurately. According to the glossary, climate model refers to a numerical simulation of climate processes, basically a set of equations and variables that represent Earth's climate and how it might change. An emissions scenario is essentially a what-if projection based on future greenhouse gas emissions, which helps model possible climate outcomes. For example, it might show me a future with less emissions versus one with high emissions. Downscaling adapts global climate models to results to a finer, more local scale. This is important because it means the climate projections are tailored to Alaska rather than more generalized global model. With this foundational knowledge, I feel more confident moving forward. Next, I'll read the guidance section for tips on using the data effectively. This guidance underscores the importance of analyzing trends, understanding extremes, and recognizing each model's uncertainty and limitations. Some of the recommendations here include using multiple models for a more robust projection and exploring additional bias correction methods, if necessary for site-specific accuracy. It even references the journal article that outlines a 6-step framework for integrating climate data into engineering, which I'll review to help me structure my approach effectively and ensure responsible and informed use of climate projections. I'm ready to access data specifically to Bethel, Alaska at this point. I'll use the search box at the bottom of the homepage and enter Bethel. I notice that the community name auto-completes and that the indigenous name is also available. Cool. Now that I've entered Bethel as my location of interest, I see the report introduction. The section emphasizes that the data I'll see is based on downscaled climate model outputs, and I can tell that it's important to remember that the data I'm about to see represent grid cells of different sizes that cover a larger area around Bethel, and that these grid cells will all have variance in elevation, slope, aspect, vegetation, and other characteristics. The spatial resolution or grid cell size may affect accuracy, as a coarse scale grid may not capture finer local variations in such factors. In this case, elevation around Bethel varies between 0 and 23 meters, but if I were working in a region with greater elevation variation, like Southeast Alaska, this could influence climate factors like temperature and precipitation more strongly. It's something to keep in mind as I interpret the data outputs. So, I need to factor in that while bias corrected, these projections may differ from local historical weather data, especially given variations within each grid cell. If I need an even closer alignment with historical records, the guidance suggests using additional bias correction techniques. To jump straight to the data I need, I'll use the table of contents. For my project, I'm looking at freezing index, so I'll select temperature indices. This section contains the projections that should help me model different thermal conditions. In this section, I'm learning that these data are derived from a 12-kilometer resolution set of climate model outputs, the NCAR Alaska Near Surface Meteorology dataset that spans a 1950 to 2099 time range. I'm hoping to use these data to improve the climate resilience of my designs in Bethel. I also see that each climate model in the list of included models represents a different potential climate future. Some wetter, some drier, others warmer or cooler, allowing me to account for a range of climate conditions under emission scenarios RCP 4.5 and RCP 8.5. This variability helps me understand not only the mean trends over time, but also the extremes, which could impact freeze or thaw depth thresholds in my thermal model. The day-met modeled baseline data informs the comparison with the future projections and is important context for these cumulative degree day indices. However, since day-met data is based on statistical assumptions rather than actual observations, I need to consider that the modeled baseline might be slightly differ from my station data values, especially where these metrics approach critical thresholds like 32 degrees Fahrenheit, 0 degrees Celsius. Now I'll review the summary table that outlines the freezing index for Bethel across different future time periods and emission scenarios. For each period, early, mid, and late century, I see minimum, mean, and maximum freezing index values along with percentage changes relative to the modeled baseline from 1980 to 2009. I see that by mid-century, 2040 to 2069, the mean freezing index is projected to decline by 38% from the baseline, but that there's substantial variability across all models and scenarios, as the decrease in freezing index from the baseline could be as much as 84% or as little as 15%. This variability across scenarios and model outputs, especially between minimum and maximum projections, highlights the uncertainty. As an engineer, I should consider designing with both the average and the full range of possible futures in mind to ensure resilience against unexpected extremes. However, I can tell from the overall trend that this significant reduction in freezing index suggests a trend toward milder winters. And this tracks with my general knowledge about climate change. Alaska's getting warmer. Looking at the data preview, I can see a snapshot of the values included in the CSV download. The data file contains annual values for the entire time series with columns for the climate model used, the emissions scenario like RCP 8.5, the year, and the degree day metric. In this case, freezing index. This preview gives me a sense of the data format and helps me confirm that it's compatible with my engineering tools. Knowing that each row corresponds to a single year and that all model runs are in the same format makes it easier to incorporate this CSV into my workflow for analyzing long-term trends or performing additional calculations. Now that I've reviewed the data preview and confirmed that it contains the information I need in a usable format, I'm ready to download the full CSV file. The download link allows me to get a detailed dataset covering the entire time series for Bethel, Alaska, including both baseline and projected values for the specific variable I'm interested in, freezing index. Download the file by clicking the download link and open it in Excel. Having this data in CSV file is convenient because I can load it directly into a data analysis tool like Excel or a programming environment like Python. This will allow me to explore trends, run statistical analyses, or even integrate this data into my thermal models. This file includes historical baseline data as well as future projections across different models and emission scenarios, giving me flexibility to compare different climate futures and understand the range of possible outcomes. Once I have the data on my local machine, I'm ready to start working with it in more depth. After reviewing the linked academic reference for these data, I've gained a deeper understanding of how the climate projections were developed and what assumptions underlie the model selection and downscaling methods. Here are a few critical considerations. The model selection process aimed to capture a representative spread of potential future climate conditions, especially for temperature and precipitation changes. This selection was deliberate to ensure that the projections reflect diverse possible climate futures, including warmer and cooler, and wetter and drier futures. As an engineer, this means that these models are not designed to predict a single outcome, but rather provide a range of plausible climate outcomes. For my work, this range is valuable because it allows me to consider both typical and extreme projections when planning for resilience. The downscaling method used for these projections is the bias-corrected spatial disaggregation, BCSD method, which balances computational efficiency with the ability to capture broad climate trends across Alaska. However, I need to keep in mind that BCSD might not fully represent certain local scale phenomena or extreme events. This adds an extra layer of caution if my design relies heavily on precise climate extremes at small geographic scales. The spatial resolution of 12 kilometers offers a practical balance between detail and computational feasibility, but it may not fully reflect finer scale variations in topography or microclimates. For Bethel, where elevation and other features vary slightly, this resolution is likely sufficient. However, if I were designing in a more topographically diverse region, I'd need to be mindful that certain site-specific characteristics might not be captured fully in this dataset. Additionally, the historical dataset used for calibration is shorter than typical datasets used in the continental United States, which can increase uncertainty, particularly for extreme values. Before I integrate this data into my project workflow, there are a few additional considerations. First, I may need to conduct bias correction if I want to align this dataset more closely with historical station data specific to Bethel. This could involve statistical adjustment to reduce any systematic discrepancies between the baseline model and the actual historical records. Doing this may enhance the accuracy of the projections when applied to local conditions. Next, I'll think about summarizing or averaging the data across models or scenarios. For example, if I want to create a single representative projection, I might calculate the ensemble mean of the various models for each emission scenario. Alternatively, if my project requires a worst case or a best case scenario analysis, I could focus on minimum or maximum projections. Finally, I'll need to consider selecting particular years or time periods relevant to my design timeline. For instance, if my infrastructure project has a 40-year lifespan, I might focus on the projections up to mid-century, 2040 to 2069.
So that's a step-by-step guide to the Arctic EDS. If you've got further questions, check out our website or don't hesitate to shoot us an email. Thank you so much to Charlie Parr for helping to develop this script, and see you in the data.